Mr. True. Okay. All right. Today we're going to be talking about integration by parts. I have lied to you all the way through Calculus 1 and part of Calc 2. There is an integration involving product rule. So if you take the derivative of f times g, you get f prime of g plus f times g prime, right? Of x, basically. If you then go, well, you know, all of our integration rules are just the inverse of the derivative rules, you can see that you have a derivative of a product is equal to a sum of two products. Integrate both sides of that equation, meaning you integrate each of those three terms. So we get f times g is equal to the indefinite integral of f prime of g dx plus the indefinite integral of f times g prime of dx. Now, if I solve this equation for either one of these indefinite integrals, we get the indefinite integral of f times g prime of dx is equal to f of g minus the indefinite integral of f prime of g dx. So in other words, this is just a quick derivation of the rule I'm about to write, a nice clean version, give you some acronym to help you figure out what role these two products are playing. But if you're finding an indefinite integral or definite integral of a product of two functions, you can actually integrate that. What you are going to have to understand, though, that, well, actually, in the past, we've already been integrating a product of two functions. But those two functions had to be created through the process of the chain rule, taking a derivative of that composition of functions. These two functions that we have multiplied together, they're not created through a chain rule process. It is some function we are going to take its derivative. So we have the integral of f, and you see on the other side we have an integral of f prime. So one of our two factors we're going to take a derivative of. And the other factor of this product, we have a g prime on the left, and on the other side of the equation we don't have a g prime show up, we have a g. So when we see an integral of a product of two factors, where those factors, that product is not a creation through the, created through the chain rule process, one part we're going to be taking a derivative of to complete the other side of this formula, and the other product we're going to be taking an integral of. And that is the basis of the idea of integration by parts. We have the integral of u dv is going to be equal to uv minus the integral of v du. Now, when you decide which of these, and the u and the dv are the two functions that are being multiplied together, so this is not written in terms of like an integral with respect to like x or something like that. When you look at the two factors of this product, the factor that you're going to integrate is going to be the most complex factor, the most complex function that you can easily integrate. U is going to be the factor of this product that when you take its derivative, it becomes a simpler function. dv, the most complex function that you can easily integrate. U, the function that when you take its derivative becomes simpler. So there's an acronym that some teachers use, and there's different versions of this acronym, but our textbook uses the LIATE acronym. So for choosing, to help you choose, U by this acronym of, and I think I like this acronym so much because I just love saying it, LIATE! Look for a logarithm in your integrand. Look for an inverse trig function in your integrand. Look for maybe an algebraic expression, like the derivative of x squared is just 2x, where the degree comes down so it's simpler. Look for a trig function, or look for an exponential. Every time I write this acronym, I want to write the first letter of the word I'm saying. We already have the E. The exponential function. And this is an acronym that the authors of the book that we're learning from and a lot of teachers use to help students go through the integration process. But I do know for a fact that some teachers do not use this acronym, and there's other variations of it. So there's not a fixed formula, if you will, that works for all teachers and students to help them go through this integration process. But I've actually never had a problem using the LIATE, or the acronym. DV is what? The most complex function that is easily integrated, because this is dv, and on the left-hand side we just have v. And u is going to be the factor that when we take its derivative becomes simpler. That's it. So let's start looking at some examples. Actually, for our first example, let's see what this looks like. We have the indefinite integral of 4x times e to the 5x squared dx. And as I've told you all in the past, we're basically, we've gotten through a ton of integration. We have like what, 17 or 18 integration rules in our back pocket. So you want to look at these integrands and find the one that it looks closest to. And while this does not meet, we see that product of two functions, and up until now when we had a product of two functions, where did the product of those two functions come from? The chain rule. So always look for that composition of functions. So what is one standout function in this integrand? The e to the power of 5x squared. If we let u be 5x squared, then du is going to be 10x dx. And does it look like we're in a good place for just simply doing the U-substitution, even though we're learning integration by parts? Some of you are shaking your head no, but what's outside the composition? What kind of function? A linear function. And what do we have in our du? A linear function. So it's not a perfect match, but if we bring this 10 over with division, and if I move this 4x out in front of the indefinite integral, we have 4. A 4 times an indefinite integral of x times e to the 5x squared dx. Well, if I want to complete the chain rule instead of, I was about to do a complete U-substitution, but there's no reason for us in BC to need to do that anymore. If I want to complete the chain rule, if I identify this u as 5x squared, I can put or create a u prime out here of a 10x, right? And if I introduce a multiple of 10, I have to balance that with a division of 10, which of course that reduces. So what is the integral of e to the u? U prime. E to the u plus c. So we have 4 over 10 reduces to 2/5. E to the u 5x squared plus c. So we need to recall, and I need another cup of coffee or a drink of coffee, that when you have a product in your integrand, the very first thing you should be thinking of is this just chain rule? Can I just do a U-substitution or create that chain rule pattern, complete it to do the problem? All right, so here's another question that looks almost the same. For our next example, we're going to have the indefinite integral of 4x times e to the 5x dx. I have a base of e in this integrand, correct? So what would be a good possible substitution, U-substitution? The 5x. So if we let u be 5x, then du is going to be 5 dx. Well, that's a problem because outside of our composition, we have a linear function. And our du is not a linear function. It's a constant. So there's not going to be a real easy way to remove this reference of x. Now, sometimes we do use this u formula twice. You know, maybe you go, well, I can get rid of this x by replacing it with u over 5 is equal to x. So let's see if we can't do a complete u substitution. If we do a complete u substitution, let's move this 4 out front. So we have 4 times the indefinite integral. We have an e to the 5x going to be replaced with e to the u. We have dx is going to be equal to 1/5 du. So let's bring that division or that multiplication of 1/5 out front and replace the dx with 1/5 du. And there would have been an x here, but we're recognizing that we don't want to have an integrand with u's and x's hanging out, so we're going to use this u formula twice and replace x with u over 5. Well, even if I bring this division of 5 out front, we still can't integrate that. So even though we went from references of x to references of u, even though we've completely removed all references of x and completed our u substitution, this is still not an integrand that we have a rule for. So you see your problem, and when you're taking any kind of standardized test like your AP exams coming up in May, you know, please do not jump to the hardest integration rules. Not everything is going to involve an inverse trig function every time you have a fraction bar in an integrand. Not every question is going to involve integration by parts. Most of your integration is going to be possible by just knowing your 17 or 18 integration rules and completing the chain rule. But that's not the focus of today's lesson. So most of today's problems, actually all of today's problems, except for our first example, are going to need to, you know, we're going to need to use integration by parts. But it's that idea of try your u sub first, realize that the easy sort of like more standard rules are not working and you have to go a little bit more complex. Whether it's in your head or you write it out, you know, but you do have to come to that realization. Please do not jump to integration by parts every single time. You're not going to need it. Okay, so this is a product of two functions that cannot be created through the chain rule process. So, liate, what part are we going to let be u? What factor in this integrand, and again I said every textbook does not use the same acronym. Some teachers don't even use that same acronym. So we may be doing questions differently and getting the same answer. But I am going to be consistent with my textbook, and I have used this liate acronym for years now, and it has been working as a teacher. So do we have a logarithmic function in this integrand? No. Do we have an inverse trig function in this integrand? No. Do we have an algebraic expression in this integrand? Yes. We have a 4x. Like a algebraic, kind of like think about more like radicals and polynomials. So we're going to let u equal 4x, then du is going to be 4 dx. Now the purpose of this is we are going to be going from an integral of a product of two functions to an expression with two terms, one of which sort of like the integration is partially complete and one we're still going to have the integral in there. So I want the dx there kind of just to see that setup. So u is going to be 4x, and then dv is going to be e to the power to e to the 5x, and then v is going to be the indefinite integral of e to the 5x dx. And maybe I should include the dx here as well. So we need to complete the chain rule. So the integral of e to the u prime. So if u is 5x, we need to introduce a factor of 5. So we have the integral of u du. And if we introduce a factor of 5, we need to balance that with a division of 5. So v is going to be equal to 1/5 e to the 5x. So let's go through the formula. Remember, this is the integral of now basically u dv is equal to, just to stay consistent with the book's notation, even though you could make variations and it still works, the integral of uv minus, or equals the product of uv minus the integral of v du. So what do we have defined as u with our little scratch work on the side? 4x. What do we have defined as v? Times 1/5 e to the 5x minus the indefinite integral of v du. And our du is 4 dx. Okay, so let's clean this up a little bit. We've got 4/5 x e to the 5x. I've got a 4/5 that I'm going to move that constant coefficient out in front of the integral. So we have a minus 4/5 times the indefinite integral. We'll leave some space here to complete the chain rule. Times the indefinite integral of e to the 5x dx. So we're taking the integral of e to the u. And e to the integral of e to the u, if that's the integral of e to the u, we need a u prime. So the integral of the derivative of 5x, why are you being so quiet, is 5. And if I introduce a multiple of 5, I have to balance that with a division of 5. So we have 4/5 times x times e to the 5x minus 4/25 times, what's the integral of e to the u? U prime. E to the u. So negative 4/5, negative 4/25 e to the 5x power plus c. This problem. So we have the indefinite integral of 4x times the natural log of 2x plus 1 dx. We have a product of two functions, yes? Okay. So do we have a rule for the integral of natural log of u? We have the integral of u prime over u gives natural log of u, but we actually don't have a rule for integrating just natural log, which is kind of crazy. We have a lot of rules that give answers involving natural log, but not a single rule that just says the integral of ln of x is. So the fact that you have an integrand with natural log in it is shooting red flags up that you're going to be needing to do integration by parts. So while the derivative of 4x is just 4, which is a simpler function, the derivative of natural log of x. The derivative of natural log of x is what? 1 over x. This complex natural log function with asymptotes and really super restricted domain becomes a rational function. A polynomial over a polynomial. Definitely an easier function. So u, following the LIATE acronym, or just the idea that derivatives of logarithms are polynomial, like rational functions of a polynomial divided by a polynomial, should be saying that we're going to let u be the natural log of 2x plus 1, and then du, what's the derivative of natural log of 2x plus 1? 2 over 2x plus 1 dx. And then dv is going to be the other factor of your integrand. So you've already talked about getting a substitution for the natural log or handling the natural log function. So dv is going to be 4x dx. V is going to be 4 times the indefinite integral of x dx. And of course, the integral of x is 1/2 x squared. So 1/2 of 4, we have v is equal to 2x squared. And you don't need the plus c when you're setting up a integration by parts. So we've got that product of two functions. It doesn't follow chain rule. And we have the integral of u dv is equal to uv. So 2x squared natural log of 2x plus 1 minus the indefinite integral of v, 2x squared du. And du is 2 over 2x plus 1 dx. All right. 2 times 2 is equal to 4, but I'm going to bring that out in front of the integrand, and we have 2x squared natural log of 2x plus 1. Bringing out the 2 times 2 is 4, minus 4 times the indefinite integral of x squared over 2x plus 1 dx. Okay. Now in my notes, I left the 4 up in the numerator, and I'm debating whether to put it back there and do the long division that way or leave it out front. It's not going to matter, but I want to stay consistent with my notes. I think I'm going to leave the 4 up in the numerator, just in case I make some silly mistake and you all don't catch it. I want to be able to catch it in my notes. All right, so we have uv times the integral of v du. Well, can we integrate? I mean, the answer, of course, is we can, but can we just straight away integrate this? No. Why not? Long division. The power of the numerator of this rational function, polynomial over polynomial, the numerator has a degree equal to or higher than the denominator. So we need to do a long division. So more scratch work on the side. At least I'm not picking the super duper short, easy ones, right? So you can get some advanced examples to help you in your homework. We have 2x plus 1 getting divided into 4x squared plus 0x plus 0. How do we turn 2x into 4x squared? Multiply by 2x. So 2x times 2x is 4x squared, and 2x times 1 is 2x. We subtract. And we have 4 minus 4 is 0, and we end up with negative 2x, plus 0 just for whatever, teaching. How do we get 2x to become negative 2x? Of course, multiply it by negative 1. So now we have negative 2x minus 1. We're going to subtract, which is going to give us a remainder of 1. So now we've got 2x squared times the natural log of 2x plus 1 minus the indefinite integral of 2x minus 1 plus our remainder of 1 over what we divided by, which is 2x plus 1 dx. What's the integral of 2x? X squared. I'm just going to do this mentally before I write any more. What's the integral of negative 1 with respect to x? Negative x. Okay, we have an integral of 1 over 2x plus 1. What does this third term look like? We're not just learning integration for the first time. I'm not writing 3 integrals. This looks like linear function constant. This is u prime over u. So if u is 2x plus 1, we need to make the numerator u prime if we can. So what's a derivative of 2x plus 1? 2. So the numerator is going to go from a factor or term of factor of 1 we're going to multiply that by 2. We're going to introduce a multiplication of 2. But if we introduce a multiplication of 2, we have to balance it with a division of 2. All right, so here we go. We've got 2x squared, natural log, once again, 2x plus 1 minus, let's keep the parentheses now so we can distribute this negative and get the right answer. You all just told me the integral of 2x is x squared. The integral of negative 1 is negative x. We have a 1/2 plus 1/2. The integral of u prime over u, now that we've completed that chain rule, is natural log of the absolute value of 2x plus 1, and then plus c. And of course, you can distribute this negative through the parentheses to simplify your answer, but you would only really need to do that if you're trying to match a multiple choice answer. All right, next example. We've got a fun one now, if those weren't fun already. There's some opportunities I have to show you some super awesome shortcuts to working through integration by parts. But to completely comprehend what's going on, we need to first realize, that the bell's about to ring. All right, for our next example, we have the indefinite integral of x squared times the sine of 7x. Always think of U-substitution first or completing the chain rule. What is U? What is the composition inside the sine? 7x. What's the derivative of 7x? What's outside the composition? Not 7. Nor a constant. We have another math function outside the composition. So this is not going to be just complete the chain rule. This is going to be integration by parts. All right. Liate. Logarithms. No. Inverse trig functions. No. That'll be coming up. Algebraic expressions. Yes. We got an x squared outside the sine of 7x. So we're going to let u equal x squared. Du is going to be 2x dx. That means that dv will be the sine of 7x, and then v is going to be the integral of the sine of 7x, dx. We just said it, but just to say it again, because I love the sound of your voices. What is u? 7x. So then u prime is 7, and we balance that multiplication of 7 that we introduced with the division. So v is going to be 1/7. Thank you. The derivative of cosine is negative sine, so the integral of sine is negative 1/7 cosine of 7x. We've got a u. We got a v. We've got uv minus the integral of v du. So let's bring out the negative 2/7 with the negative, and we got negative x squared over 7 cosine of 7x. Negative and negative is positive. 2/7 times the indefinite integral of x cosine of 7x dx. I know. Why am I not super excited? We have a u of 7x, which means u prime would be just 7. So we have the same problem we had in the first place. We've got another required step of integration by parts. So let's start again. Part 2. Woo! I love integration by parts. U is going to be x. And du is going to be 1 dx. And then dv is going to be the cosine of 7x dx. And then v is going to be the indefinite integral of cosine of 7x dx. Leave yourself room to complete the chain rule. We once again have a u of 7x, and then u prime is going to be 7. We need to balance the introduction of that multiplication of 7 with the division. So we have v is equal to 1/7. The integral of the derivative of sine is cosine. So the integral of cosine is just sine. No sign change this time. Not to save me. So we have 1/7 cosine of 7x dx. I teach this for a living. Did I even say the word sine? Maybe I said it. Did I say it? I write it, but wrote the wrong thing. Okay. Thank you. Who helped me with that one? I think that was... That was everyone. Everyone's going to deserve a point by the end of this. Why? For being here. Kind of a true statement. Calc BC at 7:30 in the morning. Yeah, you deserve a point. So we have negative x squared over 7 cosine of 7x plus 2 over 7. Now this single integral is going to become two terms. So I'm going to use parentheses, and the integral of u dv is uv. So we have an x, u is x, or x over 7 sine of 7x. So there's our uv, minus the integral of v du. V is 1/7 sine of 7x dx. Now I'm starting to run out of space. So I'm going to do a couple things here. I'm going to bring this 1/7 out in front of the indefinite integral. And once again, we have the integral of the sine of 7x. U is going to be 7. U prime is going to be 7. Balance out with the division of 7. And we have negative x squared over 7 cosine of 7x plus 2 over 7 times 1 over 7 is 2 over 49. So 2x over 49 sine of 7x. We're going to have 1 over 7 times 1 over 7, which is 1 over 7 squared, getting multiplied by a 2 over 7. So we're going to have 2 over 7 cubed. The integral of sine is negative cosine. So the negative here and the negative from that is going to become positive. So plus cosine of 7x plus c. I didn't know what 49 times 7 was, so I wrote 7 cubed. 7 times 7 is 7 squared times this 7 is 7 cubed. 249. 343. Woo! That's a lot. Okay, so every time if you have an integrand with a factor that it is either sine of u or cosine of u, and I'm sure there's other situations, but if you have an indefinite integral with a sine or cosine function, those sine and cosine functions keep going back and forth, right? The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, and you keep going in a spiral. There's a sign change, but you just keep going back and forth between sine and cosine. You would probably, right off the top of my head, which is dangerous, you're probably going to have the same situation when you have an e to the x as well. And then over here, you have an algebraic expression to some kind of power. Okay, so it's like an x to the second, third, fourth, fifth with a sine of u, cosine of u, and the derivative of e to the u just keeps coming up with another e to the u. So I probably should be double checking that, but I'm sure that's another possibility. There is a time, like you should be able to see this pattern, sine, cosine, or e to the x, and then an x to a power of 2 or greater. When that is the case, yes, sir? You are going to need to do a repeated process of integration by parts. Well, I think one nickname for this is like the tic-tac-toe method I first saw. So what I'm going to do is, it's going to look like we're doing the same problem, but I'm going to say, let's let u be x squared and dv be that sine of 7x dx. And I'm going to take a derivative of u until I get down to 0. So the derivative, so these are all going to be steps of du. So the derivative of x squared is 2x. The derivative of 2x is going to be equal to 2. And then the derivative of 2 is going to be 0. And when you get it to 0, when this polynomial works down to a constant of 0, you stop. And you need to match these 3 lines with 3 lines for v. So we're going to make basically some rows of v. So we already have done our work over there, right? So what was the integral of sine of 7x? It was negative 1/7 cosine of 7x. So our first v is going to be negative 1/7 cosine of 7x. Then, when we did our integration by parts, we had to integrate again the integral of negative 1/7 cosine of 7x is going to be negative 1/49, right? The derivative of cosine of 7x is going to introduce another factor of 7 in the denominator. So the derivative of sine is cosine, so the integral of cosine is sine, so negative 1/49 sine. And we see that in our work right here. Okay? 1/4, I mean, there was a 2x there because it was uv, but we have a 1/49 sine of 7x right there. And if we integrate this again to find a third v, the integral of sine of 7x was negative cosine. So again, we're integrating this. So we have the integral of sine is negative cosine. Okay, so with this table of values of u's and v's, the integral of u dv is, what's the first term? U times v. So this is u and this is v. So we're going to multiply down and do u times v and get negative x squared over 7 cosine of 7x. And in our line of work over here, we had a uv, but then we had another integral that we had to set up, right? We had another required step of integration by parts. So we redefined another u, we found another v, and we finished the product, or finished the work, but when we did another integration by parts, after setting up u and dv, we had another what? uv. So we're going to have another step of u, another u, times another v. But it was minus this indefinite integral. So we had like a -1. Now I did some work, and all this is kind of getting a little bit convoluted because we had a negative come out of the integrand. But it was minus u dv. And that one term became 2, and then you had to distribute the negative sign through it. This negative has to get distributed through a binomial. So when you do this sort of like tic-tac-toe method for shortcut process of multiple steps of integration by parts, when you do that first u times v, you're going to leave that product as is. When you do the second u times v, you're going to have to multiply that by -1 or have a sign change. That's from this minus in the formula, minusing one term. If you have to do integration by parts, that one term becomes 2, and you have to distribute the negative into that and it's not a binomial, but into those two terms. You have to distribute. And then you have a third step, right? Because we had to do integration by parts to begin with. Then we got an integral that required integration by parts again. And then we had a third integral that we just had to complete, right? So that's going to set up another UV. So we're going to have 2x times negative 1 over 49. So negative, or that's going to be, stick with me for a second, 2x times negative 1 over 49 will create like a negative term, but we have that sign change. So negative, positive times negative is negative, times negative is positive, and then we have that 2x over 49 sine of 7x. And then we go back to a positive or a product that you don't change the sign of. So we have 2 positive times positive, and we keep it positive. So 2 times 1 is 2 over 7 cubed cosine of 7x plus c. And unless I've done something crazily wrong, that is the final answer. So when you have an integrand that has an algebraic factor of like just an x to a power of 2 or higher, and your other factor, I hope I don't have to edit this out of the video, but is either like a sine of u, cosine of u, or e to the u, where the sine and cosine go in a circle and e to the u just keeps giving you back e to the u, you know, okay, there's some kind of like chain rule situation. But you can set up like a little table of values of u and then go du, du, du until you get to some constant of 0, and then keep integrating your sine, cosine, or e to the u until that first column comes out to an answer of 0. And you can just literally connect the dots and write your answer, which is really freaking cool. Yep. So if this were to the 5th power, it'd be like 4th, 3rd, 2nd, so on and so on and so on. As you connect these and multiply these products of the u and the v and the u and the v and the u and the v, these keep alternating back and forth. Because you're going to repetitively have that going back to the formula, which doesn't, it almost doesn't even feel like that's what we're doing, but you know, you have a subtraction of that integrand, which becomes 2 terms, and that negative has to keep getting distributed through those ever-expanding terms as you redo over and over and over again the integration by parts, giving you 1 term into 2. Here we go. We should have alarm bells going off all over the place. As we take derivatives or integrals of sine and cosine, what do we keep doing? Going in a circle. We just never stop doing math because we keep going back and forth between sine and cosine with some sign changes, of course. What's the derivative of e to the u? E to the u. Yay! So let's see what happens. What are we going to let... I don't think we have a great thing going on here. Do we have any logarithms? No. Inverse trig functions? No. Algebra? I mean, this is all kind of algebra, but this is trig, and some may call it like a transcendental function or exponential growth. It's just sort of algebra, but it's not like a polynomial. Do we have trig? Yeah. Honestly, I don't think, it's not really going to make much of a difference if you let u be e to the 2x or cosine of 3x, but to stay consistent with my notes in case I make some silly mistake, we're going to let u be the cosine of 3x. And then, of course, du, the derivative of cosine is negative sine of 3x. You got to finish the chain rule. So basically negative 3 sine of 3x dx. And then dv will be e to the 2x dx. V is going to be the indefinite integral of e to the 2x dx. We have to finish the chain rule. So introduce a u prime and balance that with the division of 2. And v is equal to 1/2 e to the 2x. And let's go. So we have u v, so 1/2 e to the 2x cosine of 3x minus the indefinite integral So that's uv times the indefinite integral of v du. So negative 1/2 e to the 2x times negative 3 sine of 3x dx. Okay, so let's clean this up a little bit. You're going to see that we haven't gone very far. So we have 1/2 e to the 2x cosine of 3x. Negative times negative is positive, so we're going to have plus 3 over 2. Plus 3 over 2 indefinite integral times the indefinite integral of e to the 2x sine of 3x dx. You were practically right back to where we started from, except we have a sine function instead of a cosine function. So we have no choice but to do the integration by parts again. Yes, it will. What was that? Won't it just loop? Yeah, it is. That's what's so fun about this problem. We get to go in a circle. So now u is going to be that trig function again. So the sine of 3x, that's why we're doing this as an example. Du, what's the derivative of sine of u? Cosine of u prime. And then dv is equal to e to the 2x. And basically that's exactly what we had before, so I'm just going to write the answer. V is 1/2 e to the 2x. So let's do the expansion again. And Mr. Smarty Pants over there already recognized that there's going to be a pattern. So because you said the word looping, I'm going to go back and write the original problem to begin with as I write the next line. So the original problem, the indefinite integral of e to the 2x cosine of 3x dx is equal to 1/2 e to the 2x cosine of 3x plus 3 over 2 times uv, so 1/2 e to the 2x sine of 3x minus the indefinite integral of v 1/2 e to the 2x du times 3 cosine of 3x dx. So much fun. Indefinite integral of e to the 2x cosine of 3x dx is equal to 1/2 e to the 2x cosine of 3x. 3/2 times 1/2 is 3/4 e to the 2x sine of 3x. Now, in our integrand, we have a 3 over 2, and I want that to come out because I need this, what like I said, isn't this going to loop? I need an e to the 2x cosine of 3x dx to show up. Like I want that same thing. So we do have that e to the 2x cosine of 3x. So the 3/2 is going to come out with a negative, but it's also going to get multiplied by 3/2. So 3 over 2 times negative 3 over 2 is negative 9 over 4 times the indefinite integral, just making sure I'm not making a mistake, e to the 2x cosine of 3x dx. We might as well stop because we're right back to an integral that's an exact match. The integral of e to the 2x cosine of 3x. That is the same integral that we had in the original problem. That's the question we were asked in the first place. But we have, except for the coefficient difference, we have the same indefinite integral on both sides of the equation. We're going to move this indefinite integral from the right-hand side over to the left-hand side. And we're going to get 4 over 4 plus 9 over 4 is 13 over 4 times the indefinite integral of e to the 2x cosine of 3x dx is equal to 1/2 e to the 2x cosine of 3x plus 3/4 e to the 2x sine of 3x. Now I need to put the plus c because I've isolated the indefinite integral. And your last step is to just do what? Multiply both sides by 4 over 13. So we have the indefinite integral of e to the 2x cosine of 3x dx is equal to 2 over 13 e to the 2x cosine of 2x, 3x, plus 3 over 13. I'll probably write this do this faster by just looking at the work. E to the 2x sine of 3x plus c. Now that's a little bit of work. Just a little bit. But, hey, stop it. Your phone doesn't take a test. You do. And I got a little secret. We can do this much quicker. Check this out, sucker. What did I tell you when we have, when we realize sine and cosine keep going in a circle and, derivatives and integrals of e to the u just give you another e to the u. You should look at this and alarm bells be screaming that I'm probably going to need to do integration by parts multiple times. So check this out. We're going to let you, tic-tac-toe, we're going to let you be, okay, your homework is going to be to do this in the reverse pattern and see if it comes out to be the same, because my notes has you being e to the 2x. And if I do make a mistake, I want to be able to check or correct myself. So we're going to let u be e to the 2x. But Mr. True, you said let trig be first. But I also said this was it's not steadfast rule. So I'm going to let u this time be 2x in case I make some silly mistake when I'm in a rush. I can check my work. If u is e to the 2x, then I'm going to make a bunch of du's. So the derivative of e to the 2x is 2 times e to the 2x. And what's the derivative of e to the 2x? 2. What's the derivative of 2 times e to the 2x? 4 times e to the 2x. What's clearly not going to happen with my u column? It's not going to go to 0. So before I go too far, I'm going to start working on my dv column. So if dv is then equal to, now I've let u, for some reason I flip-flopped this in my notes, but if u is e to the 2x, then dv is cosine of 3x. And v, we're going to make a bunch of v's now. Let's do some scratch work that I'm going to erase. The integral of cosine of 3x dx. If u is 3x, then u prime is 3, and we have a 1/3. So what's the integral of cosine of u prime? The sine of u. The derivative of sine is cosine, so the integral of cosine is sine. So we have 1/3 sine of 3x. Okay, let's keep going. We're going to keep the dv column going until we're back, we're creating new v's. We're going to keep creating new v's until we get back to cosine. So we're going to take the integral of 1/3 sine, we're going to take the integral of 1/3, the indefinite integral of sine of 3x dx. We have a u of 3x, so we need a u prime of 3, which means we need to balance that with a division of 3. And the integral of sine is negative cosine. So we have a negative 1/9 cosine of 3x. I'm going to stop here because I'm back to cosine, which, even though I'm doing this in reverse order, like in terms of what u and dv are, but we stopped our u sub until when we got another cosine of 3x and someone said this isn't just going to loop. So we're going to multiply. When we did this, when we realized that we have to stop and do a loop, this has to be set equal to the original integrand to begin with. And with this being a horizontal multiplication, we're not actually finishing, we're not actually setting up. That's going to be u, and this, for this u, is not going to be v, it's going to be dv. So stopping here and realizing that we have a loop means that we need to write the original problem, which is the integral of e to the 2x cosine of 3x dx is equal to that first product of uv, e to the 2x over 3 sine of 3x. Our next uv, which is positive times negative is positive, so plus 2 over 9 e to the 2x cosine of 3x. And then what I forgot was we need to recognize that this is not u times the next v. It's this, for this u, this is a dv. Like if you go horizontally, even to begin of the table, I said this is u, and dv is cosine of 3x. So when you go horizontal, it's not u times v, u times v, u times v. It's u horizontally times for its dv. So this is an integral that's not complete. So we have still a positive situation, but this is going to be positive times negative is negative. We have a 4 over 9, so negative 4/9. I'm already moving that out of the integral because I just looked at the solutions. Times the indefinite integral of e to the 2x times a cosine of 3x dx. And then that has to get added over to the other side, and 9 over 9 plus 4 over 9 is 13 over 9. Oof, I thought I made a major mistake there. 13 over 9 times e to the 2x, 13 over 9 times the indefinite integral of e to the 2x cosine of 3x dx is equal to e to the 2x over 3 sine of 3x plus 2 over 9 e to the 2x cosine of 3x plus c. And then we multiply both sides by 9 over 13. We have the indefinite integral of e to the 2x cosine of 3x dx is equal to 9 over 3 reduces to 3 over 13 e to the 2x sine of 3x. 9 over 9 reduces to 1. So we have 2 plus 2 over 13 e to the 2x cosine of 3x plus c. Please tell me that's the same answer. Yeah, it is. 2 over 13 e to the 2x, 2 over 13 e to the 2x cosine of 3x, and 3 over 13 e to the 2x sine of 3x. We have the same answer. Whoop, whoop. And in blue and red, we got a lot less work than we had in black. That's sweet. So it takes a long time to I didn't have to really work both of these problems two different ways, but the intention here is to let you see the long process of multiple steps of integration by parts and the looping that we really noticed. And I want you to see that with the tie-in of this sort of shortcut tic-tac-toe method, which is awesome when you can use it. I just want you to see how it works. And we unintentionally had a little bit of variation in what we let be u. Like I said, the Leate rule is not set in stone. It's a tool that you can follow as a guideline. Okay, so for our last example, we have a definite integral now of the definite integral from 0 to 1 of 3x times the inverse cosine of x squared dx. So going back to Leates, because, well, we are doing integration by parts. Do we have logarithms? Do we have inverse trig functions? Well, actually, we finally have an example that includes that, the inverse cosine of x squared. So we are going to let u be the inverse cosine or arc cosine of x squared, which means that du is going to be, well, the derivative of inverse or arc sine is u prime over the square root of 1 minus u squared. And when you have these memorized, these derivatives involving inverse trig functions, the sine, the tangent, the secant, those primary trig functions, they all have positive derivatives. The cofunctions, cosine, inverse cosine, those are the same except they just have some, negative answers, negative u's in the numerator. So if u is x squared, then u prime is 2x, but because it's not sine, it's cosine, it's negative 2x over the square root of 1 minus u, our u is x squared, squared. So recalling these derivative rules involving inverse trig functions. So du is going to be negative 2x over the square root, basically, of 1 minus x to the fourth dx. And then dv is going to be our 3x, or we can bring this 3 out. Let's go ahead and do that. Let's bring this 3 out in front of our definite integral and just have our du, or dv, excuse me, be x. And then if dv is x, then of course v is going to be 1/2 x squared. 1/2 x squared. So now, I really don't like doing or using that definite integral notation with an integration by parts. I can get a real bad habit of losing one of my limits or a set of limits somewhere in my work. So I'm going to go ahead and do all of my indefinite integral work on the side, and when I get my answer, I'm going to come back and pay attention to those upper and lower limits of 0 and 1. So the indefinite integral of x times the inverse cosine or arc cosine, the inverse cosine of x squared dx is going to be equal to u v, so 1/2 x squared times inverse cosine of x squared minus the indefinite integral of v, so 1/2 x squared du. So that's going to be times negative 2 x over the square root of 1 minus x to the fourth dx. So we have a negative times negative will be positive here in a second, and the 2 divided by 2 is going to come out to be 1. So we've got 1/2 x squared times the inverse cosine of x squared. Negative times negative is positive, so plus an indefinite integral of x times x squared, which is x cubed, over the square root of 1 minus x to the fourth dx. And you might start seeing here that inside of our composition, the square root, we have a 1 minus x to the fourth, and outside that composition, we have an x cubed. So it's looking like that we can set up a U-substitution formula or process, and we hate working with radicals. So I'm going to rewrite this, bringing the radical out of the denominator and writing that as a power of, well, negative 1/2, because we're bringing it out of the denominator. So we have the indefinite integral of x cubed times 1 minus x to the fourth raised to a power of negative 1/2 dx. Now, if u is 1 minus x to the 4th, the derivative of that u is going to be 4x cubed. So we need to complete that chain rule and get a u prime outside the composition of this power of negative 1/2 and get that to be negative 4x cubed. So the derivative of negative x to the 4th is negative 4x cubed. So introducing a multiplication of negative 4 means we need to balance that with a division of negative 4, giving us a coefficient out front of negative 1/4. So we've got 1/2 x squared times the inverse cosine of x squared minus 1/4. The integral of u to the n, u prime, is going to be u to the n plus 1. So we're going to add 1 to this negative 1/2 power and have a base of 1 minus x to the 4th now raised to the 1/2. Of course, we raise that power up by 1 and then divide. Well, dividing by 1/2 is the same as multiplying by 2. And I'm going to go ahead and put the plus c over here because I'm doing my integration as an indefinite integral right now. And we have 1/2 x squared times the inverse cosine of x squared. Of course, 2 times 1/4 is negative 1/2, with the negative there already, times 1 minus x to the 4th to the 1/2 power plus c. Let me check my work, make sure I'm not making a mistake. Looking good. Now I'm going to bring this up now that my indefinite integration process is done, and we're going to reintroduce these limits. So we have 3 times 1/2 x squared times the inverse cosine of x squared, I'm saying that a lot in this example, minus 1/2 times 1 minus x to the 4th to the 1/2. I don't need a plus c now because I'm going back to my definite integration notation where we have those upper and lower limits of 1 and 0. To simplify that arithmetic we're about to run through, I'm going to go ahead and take this 1/2 common 1/2 factor and factor that out and have 3/2 times x squared times the inverse cosine of x squared minus 1 minus x to the 4th to the 1/2 power with those upper limits of 1 and 0. Let's get those limits plugged in, and we have 3/2 times 1 squared times the inverse cosine of 1 squared, which is 1, minus 1 minus 1 to the 4th, which is 1, to the 1/2 power, and then minus, let's plug in the 0. You might see what some of these answers are going to come out to, but if you do too much in your head at the same time, like sometimes I do, and you'll make some kind of small mistake which throws off your final answer, let's plug in the 0. So we have 0 squared is 0. Okay, well 0 times anything is 0. So this whole first term, when we substitute in 0, is going to be 0. And then minus, parentheses, 1 minus, substituting that at 0, 1 minus 0 to the 4th, which is 0, to the 1/2 power. Clean this up a little bit. The inverse cosine of 1. What angle measure gives you a cosine value of 1? Cosine of 0 radians is 1. So the inverse cosine of 1 is 0. So actually, this first term is going to come out to be 0. Of course, 1 minus 1 is 0. And then over here, we've got the square root of 1, which is 1. And negative times negative is positive, so we have a positive 1. So 3/2 times 1 is 3/2. And that's how I like to work out problems, definite integrals, that I realize ultimately involve integration by parts. I'm going to work those out on the side as an indefinite integral. And when I get my answer, then I go back to the definite integral, write my answer from the indefinite integral, apply the upper and lower limit, substitute those in, and in our last example, again, we have that answer of 3/2. Bam! Go to your homework.